Hi. In this problem, we'll get some more practice working with joint PMFs and calculating conditional expectations, conditional variances, thinking about independence between two jointly distributed random variables, and more practice along those lines. So here is the joint PMF between two random variables x and y that were presented in the problem. And in the beginning, we're given them in terms of some constant c. And the first part of this problem, part A, asks us to find out what exactly this constant is. So how do we calculate this? Well, we know that the sum of all these probabilities has to equal 1. So when you sum over all the x's and all the y's of the joint PMF, you know that this has to equal 1. And well, let's just add these up then. We have 1, 2, 4, 6, 10, 13, 14, 20 c's. So the sum is 20c, and we know that it has to equal 1. So that tells us that c is 1 over 20. Okay, so that wasn't so bad. Just using this identity to calculate what the c is. So now we know exactly what all these numerical values are. And now the second part of the question asks us to find a marginal. So what is the marginal PMF of y evaluated at 2? What does this actually mean? Remember, to calculate this, what we do is we take the joint and we add up all the x's, holding y fixed at 2. And what this really amounts to is just taking this row where y equals 2 and adding along this row, across this row. And so what we have is we have 2c plus 0 plus 4c, so that gives us 6c. And we know what c is, so the answer is going to be 6 over 20. Okay. So just some simple exercise calculating what these marginals are. And if you wanted to calculate the marginal of x, you would sum along these columns instead. Okay, so now we define a new random variable. We call it z. And z is defined to be y times x squared. And what we're asked to find is the conditional expectation of z given that y is equal to 2. All right. So, well, the first thing we can do is we can substitute in. We know that z is y times x squared, right? So, and the PMF that we have is in terms of y and x, so let's substitute those in. And now the next step is, well, we're given that y equals 2. So this y is no longer really random. We know that it's equal to 2. So we can substitute that in. So we did that. But notice that we still keep this conditioning on y equals 2. And the reason is that this conditioning still affects x because y and x are not independent, or at least we haven't verified that yet. So we need to, in general, keep this conditioning because it may affect the expectation of x. Okay, so this is just a constant, so we can also just pull that out. So what we really need to do now is find this. We need to find the expectation of x squared conditioned on y equals 2. All right, so how do we do this? Well, remember that to calculate these conditional expectations, what we need are conditional PMFs. And so what we really need to do here is figure out, this is actually going to be require calculating what the conditional PMF is. So let's figure out what this conditional PMF is. All right, let's go up here. What is the conditional PMF of x given that y equals 2? So that we know that the conditional is the joint divided by the marginal y equals 2. All right. So now we know what this denominator is. Probably the y equals 2, we calculated already in part B. So what now is this part? The numerator we also know because it's in the PMF, the joint PMF that we're given. So now let's figure out what this is. So given that y equals 2, we know that we can focus on this row right here. And in that row, x can be either 1 or 3. Right? Because x, given that y equals 2, x has 0 probability of being 2. All right. So we know that x can take on 2 values. So x can be 1 or x can be 3. Right. So in the numerator, in the denominator, we know that this is equal to 6 over 20. And the numerator is the probability that x is equal to 1 and y is equal to 2, which corresponds to here, which is 2 over 20. So we know that this is equal to 1/3. And similarly, for x equals 3, it's 4 over 20 over 6 over 20, which is equal to 2/3. So we figured out what the conditional PMF is. A simple way of eyeballing this is also just, we know that it focuses on us on this row, and you know that when conditioning, it basically rescales the probability so that they add up to 1. So we know that, well, the total is 6c, and two of those are for x equals 1, 4 of those are for x equals 3, so it should be in the ratio of 1 to 2, which gives us 1/3 and 2/3. All right, so now we know this, and we can actually calculate out what this conditional expectation is. Remember, for conditional expectations is equal to, it's going to be the value squared times the conditional PMF at that value. So the value, we can take on 2 values, 1 or 3. So for 1, it's 1 squared times the conditional PMF at 1, which is 1/3. And for 3, it's 3 squared times conditional PMF at 3, which is 2/3. So the final answer that we get is 2 times 1/3 plus 1/3 plus 6. Right. So it's 2 times 1/3 plus 6, which gives us a final answer of 38 over 3. And that gives us our conditional expectation of z given y equals 2, which is what we wanted. All right, so that is part C. And part D asks us a more, less mathematical question, but more intuition. So the question asks us, suppose that we know that x is not equal to 2. So we condition on the fact that x is not equal to 2. And we're asked, in that conditional universe, are x and y independent? Well, so because we know that x is not equal to, let's forget about this column. And so we only have these 2 columns remaining. And in that universe, how do we know if things are independent? Well, one way to tell is they're independent is that knowing what x is does not affect the probability distribution of y. And so is that the case in this conditional universe? Well, if I told you that x equals 1, then the probability distribution of y would be in the ratio of 1 to 2 to 3. Right? So when you renormalize that, the marginal, the conditional would be, PMF of y would be 1/6, 2/6, 3/6. And if I do this if I tell you now that x equals to 3, we again have a ratio of 2 to 4 to 6, which is the same as 1 to 2 to 3. And so we would, again, when we renormalize this, we would get 1/6, 2/6, and 3/6. So what we've discovered is that if I tell you that x is not equal to 2, so x is either 1 or 3, then any further information about what x is doesn't really tell you anything more about what y can be. So if I tell you that x is 1, then you know that y has a 1/6 chance of being 3. if I tell you that x is 3, y still has a 1/6 chance of being 3. So because that is the case, then x and y are actually conditionally independent, conditioned on x not equal to 2. All right, so the shortcut for looking at this is to see whether or not one of these columns are multiples of one another. And if they are, then they will be conditionally independent. You can also do the same thing and ask yourself, if I tell you what y is, does that change the distribution of x? Well, x can't be 2, so forget about that. Now look at these ratios. It's 1 to 2, 2 to 4, and 3 to 6, which are all the same ratio. And so, again, knowing what y is wouldn't change the distribution of x, so they are independent. Okay, so the last part of this problem is a question about conditional variance. And specifically, we want to find the conditional variance of y given that x is 2. So we want the variance of y given that x is 2. All right. So in order to do this, how do we calculate this variance? Well, calculating this variance is kind of the same as calculating a normal variance without the conditioning. It's expectation of y squared, condition on x equals 2, minus expectation of y, condition on x equal 2 squared. So recall that a standard variance, variance of y, would just be expectation of y squared minus expectation of y quantity squared. The difference in the conditioning is that just you carry over this conditioning in both of these terms. All right, so now what we need to do is just calculate what these two terms are. And in order to do that, we need the conditional PMF of y given that x is equal to 2. So what we need is the PMF of y given that x is equal to 2. All right. So what we're in this world, the world of this middle column, where x is equal to 2. And so let's take a shortcut now. We know that we can go through all the steps, but we can see that, well, when x is equal to 2, y has can neither be 3 or 1, and they have the equal probability. And so this conditional PMF must be probability of 1/2 being 1 and 1/2 being 3. Right, because we're just taking this and rescaling it so that it adds up to 1 and becomes a valid PMF. All right, so we have this conditional PMF of y now. We can use this to calculate these two terms. So the first term, remember what we do is we take this y squared and we apply it to this expectation. So it's going to be, for y equals 1, it's going to be 1 squared times the probability that y equals 1 given x equals 2, which is 1/2, plus y can also be 3. You square that and multiply the probability that it's equal to 3. All right, so that's that first term. Now the second term is the probability that, well, y can be 1 with probability 1/2, and it can be 3 with probability 1/2. So that gives you the conditional expectation, and then you square it. All right, so what do we end up with in the end? We get 1/2 plus 9/2, which gives us 5. And you subtract out 2 squared is 4. So it turns out the conditional variance in the end is 1. All right, so we've gotten some exercise here with all kinds of calculations related to a joint PMF. We've used normalization to find out what the constant should be. We've calculated some marginals. We calculated conditional PMFs, conditional expectations, and conditional variances. And we've also thought about independence between two jointly distributed random variables. And so for these concepts, it's useful to do a lot of these kind of drill problems just to really cement these ideas in your head. All right, so I hope that was helpful, and we'll see you next time.